Hey, howdy everyone. This is part 3 of lecture 2 on workflows for subsurface modeling. Now, we've already previously covered in the first lecture all these concepts around basic workflow design, and in the second lecture it was a demonstration of how to work with tabular data in Python. Of course, that would be the case for well data, which would be a table of values. Now I'm going to talk about how do we work with gridded data in Python with a demonstration in Jupyter Notebooks. Now, why do we care about gridded data? Well, we often work with maps. We often work with two-dimensional information, three-dimensional information, seismic attributes, geologic maps, or maybe we have full three-dimensional representations of trends. The models we build are also in 3D and are often on regular grids. So this is our gridded data in our subsurface modeling workflows. And so once again, we return to Jupyter Notebook, and we're working with a Python Jupyter Notebook that's been put together for the purpose of demonstrating working with gridded data structures, or ND arrays, in Python for engineers and geoscientists. Now, this is available at this link right here. It's within the Geostats Guy account on GitHub, within my Python numerical demos repository. The file is Python data basics _ data frame IPY NB. Python notebook. Okay, so this right here is a bit of a preamble explaining the motivation, giving a little bit of details. In general though, if we're talking about gridded or regularly sampled data structures, we're talking about something represented by an array, a matrix of values. And so what we'd expect is that we have two-dimensional, in this example we'll show in 2D maps. And so we have two different dimensions going from 1 to n1, 1 to n2. Specifically, I should mention, though, that in Python, these indices are actually represented by 0 to n1 minus 1, 0 to n2 minus 1. Python is just like C++. The default indices are going from 0 to n minus 1, as opposed to Fortran, which likes to go from 1 to n values when you are referencing values within an array. All right, so in order to get started, the first thing we need to do is load up some packages. As with the previous example, we had to work with OS so we could set the current directory. We also worked with NumPy, which we stated we'll just refer to it as NP for short. And now we'll work with matplotlib, pyplot functions, which will represent as plot, PLT I should say, and we also want to work with scipy, which we will import from it the stats sub part of the package, so that we'll have access to all of the stats type methods. Okay, so now I should mention right here in advance is that if you want to hear more about the basics of working with Jupyter Notebooks, I'm not going to repeat that here. I speak a little bit in the first couple minutes of the last lecture about the basics of the blocks, the markdown, the code, and running it, and so forth. So let's go ahead and run that block. We run that block, you can see the star there while it's running. The circle was solid. Now it's done running, no errors. Good. We got everything in place. The libraries we need to work with are available to us from the packages. And so we can go ahead and start. Now, this is different than the last one because we're going to start using some of our own functions. And so we'll include 3 functions. And so specifically, ndArray to gslib, gslib to ndArray, and pixelplot. Now, these 3 functions actually come directly from GeostatsPy, which is really just a set of functions that allow us to work with geoslib type of methods in Python really efficiently. Pretty simple, keeping all of the conventions of geoslib. So this function right here allows us to take an ndArray, which is an array in Python, the NumPy package, and we convert it to a geoslib file. A geoslib array is just represented as a single column of values that sort first on X, then Y in the two-dimensional case. It has a little bit of a header on it. It's not a big deal. It's a flat ASCII file. This program will create that file. Why do we want to have that? Well, when we work with geoslib functions later on, we're going to want to be able to create gridded data files, models, and so forth, inputs, for the purpose of running those files and to read them back in. To read them back in, we have the geoslib to ND array program. It will read a geoslib output file, which is in the GeoEAS format, from a 2D case into a 2D NumPy ND array. And so this is pretty convenient. The pixel plot method just uses standard matplotlib, which is really nice. It's a package that allows us to do plotting using the same type of methodologies as MATLAB. Has quite a bit of flexibility to it. Now, a lot of people who came from geoslib or not had experience with matplotlib may struggle with it. And so that's why I create simple functions for histograms, pixel plots, and so forth that use conventions that are more similar to geoslib. Very straightforward for a beginner. Okay, as always, we need to run those functions. So we'll click on that block. The green square indicates we've clicked that as the current block and run it. Run it, no errors. So now these functions exist in memory. We can call these functions anytime we like, and we will. So we set the working directory. We do that, as I mentioned before, so that we don't have any issues with files disappearing, not knowing where we're loading files from, getting confused, having to write out full directory addresses every time can be a bit of a pain. So we'll set a current working directory. You can, of course, reset this anytime and work with a variety of different directories for a more complicated workflow that spans multiple directories. Go ahead and run that. We have the current directory. Let's do a simple load. Now, our gridded data file, porosity_truth_map.dat, is a comma delimited two-dimensional matrix file. Now, I showed that example in the first lecture. It's a very straightforward type of file structure. And if we go ahead and run this command, we got no errors. So porosity map now exists as a two-dimensional NumPy ND array. And so how do we figure out what it is? How do we kind of get a sense of what's going on? The shape command will tell us the actual number of dimensions and the extent in each dimension. We run that. We have a one-dimensional, and now I think I have to correct myself. I think I said 2D. Nope, we loaded it as a 1D ND array of 10,000, which is 100 times 100. So that makes sense. If we have a 100 by 100 2D array, but we've just sorted it into a one-dimensional array, the result is a 10,000 by 1 one-dimensional ND array. Now, we might be interested in, can we go ahead and get it to the two-dimensional form? And we can do that in a quite straightforward manner with the NumPy member function reshape. Reshape has parentheses because it takes multiple parameters. It takes parameters, I should say. And the first parameter is simply going to be the array that you want to reshape. The next parameter is going to be it will include the dimensions that you want to reshape it to. We put in square parentheses because it's going to be passed along as a single array of values. And so we want 100 by 100. We're telling it we want it two-dimensional, 100 by 100. Then in order to check to see what we've created, we can access the member of an ND array shape, and it will report to us in a tuple the dimensions or the number of cells or entries in each dimension. Now, we can go ahead and access that shape, and we can gather the first value. That will be the number of rows, and or NY in the vertical direction, I should say, the number of cells in the vertical direction, and NX, which will be the number of cells in the horizontal direction if we're looking at it on the screen. I should have mentioned that I switched these just now because I often have the habit of mixing up n, x, and y because the convention in Python ND arrays is first the y, then the x, but in GSLib it's x then y, and I'll sometimes make that mistake. But I'll get it straightened out. So let's go ahead and run that command. If we run the command, what we get is 100 by 100. That's our tuple. Now if you look up a definition of a Python tuple, it's a collection which is ordered and unchangeable. So the output from this is going to be really like a set of values that have a distinct order and meaning. And so this is ny, nx, and if we had z and so forth, we could carry on through multiple dimensions. Now, we can also check, and we'll see that once we've done the reshape command and we grab ny and x and we plot them up, we can see, yes, it says the number of cells is 100 by 100. So we've got that figured out. We've got, in fact, loaded our map, our grid, regular gridded data, and we've converted it to, it was loaded as a one column, and we've converted it to a 100 by 100 array. So we'd be good to go to visualize and so forth. We'll do that shortly. Now, of course, you might be interested in closing the loop, because it's one thing to load data, it's another thing to save data, and we want to make sure that that works both ways. So let's go ahead and use the built-in function for ND arrays known as toFile. It will take our porosity map, which is an ND array, and it will save it out as this file right here. Now once again, we can repeat the command that we used before, the from file command, to load that which we just saved back into a new ND array called porosity underscore test. And we can then compare the results of the loading back in of the array with what we had originally by using the numpy built-in function array equal. This array equal will compare two arrays to each other and will return true, which we say check is equal to that. So check is now our variable that'll tell us whether it's true or false, and it's based on whether or not these are two arrays are equal to each other. Now, the porosity map was already reshaped to be 2 dimensions, but the porosity test was left as a 1-dimensional array. So we can use the flatten command, which is a built-in command for an ND array, which will convert a multi-dimensional array into a 1-dimensional representation. And so now we can compare these as apples and apples, compare them to each other, and let's see what happens with our completing the loop. The array we wrote out and the one we read back in are the same. We close the loop true. So we got a true value for check. So when we took the check variable, which is Boolean, true or false, coming out from the ND numpy array underscore equal command, built-in command, we can go ahead and convert it to a string, and we can append it into the string right here with the plus symbols, and there we go. We get a nice little write-out that tells us, yes, we closed the loop, it was fine. Now, you might be interested to actually save your array as a 2-dimensional comma-delimited file. And I showed that example in lecture number 1. It's pretty straightforward. So we can go ahead and use the save text command. The name of the comma-delimited file, porosity underscore map, CSV, the name of the 2-dimensional ND array, and then the delimiter we want to work with. Comma delimited, we just put a comma in the quotes. If we run this command right here, we'll in fact create a 2-dimensional array that you can actually load that directly into Excel. A comma delimited file, CSV file, will actually load automatically into Excel. It will fill up 100 by 100 cells with the values. You could actually take conditional formats and get a sense of what this data set looks like. You could work directly with it in Excel if you wanted to. So now it would be useful to just go ahead, load this back in. We always like to close the loop and make sure we're able to save and load, and that what happens after we save and load and come back is exactly equal to what we had before. So let's go ahead and do that. The load command for the 2-dimensional comma delimited array, or any type of delimited array, would be load text, and just the name of the file and the delimiter that we're working with, comma again. And that'll create our 2-dimensional ND array. And we can go ahead, because it was a 2-dimensional comma delimited file, it'll actually create an ND array that's two-dimensional. We don't have to do any reshaping. And so we can perform our test again with the numpy command, built-in function array underscore equal, and we can compare the original two-dimensional ND array to the loaded two-dimensional ND array based on us saving that two-dimensional array and reloading it back in, and we can print the test result. The test result's true, they're equal, we're good. One more time, we'll do another save and load, but this time we'll use the methodologies that we had declared above, the function we declared above. And so we'll perform that with the nd to 2gslib command, which is part of the geostats pi set of functions that helps us work directly with geoslib in Python. And so we'll take our porosity map and we'll save it as porosity underscore map underscore geoslib.out, and we'll give the name of the column as porosity. That's recorded as part of the geoslib GeoEAS file format. It needs a name for the property. So we go ahead and save it, and then we'll load it back. The geoslib to ND array will load that file. We have to tell it to load the first column because we can select any column within that file. There's only one column. Remember, in Python, the first column, the first index is always 0, so that means first column. We specify n, x, and y so that this command knows exactly what are the dimensions of the two-dimensional array that it's about to create. Otherwise, it wouldn't know exactly the size or shape of the array. I should mention that geoslib stores gridded data in a single column, sorted first by column, and then over the rows going from the bottom up. So it has its own convention. The program, the function for geostats pi accounts for that, takes care of that. Now, it's not very satisfying to load and work with loading and saving all of this two-dimensional grid data with all these different methodologies and never look at it. If we have gridded data, we of course want to look at it. Now, in order to display it, we have to specify what's the grid coordinates. We have to understand also what are the minimum, maximum variable values, what's the specific color map we want to work with. And so this line of code is taking care of all of that. Now, if I haven't mentioned it already, with Python you can put a semicolon, and that way you can place multiple commands on the same line. And that's pretty useful because all of these are very simple. We're just setting a bunch of different variables to different constant values. And so we don't want to create a big long box. To do that, we can do it all on one line. Xmin, Xmax. We have a 1 kilometer in the X direction, 1 kilometer in the Y direction. That's all it means. That's the extent of the grid that we're working with. The individual cells are assumed to be isotropic. They're squares. They're not longer one direction than the other, and so they're 10 meters. We got 1 kilometer by 1 kilometer by 1 kilometer, and we have 10 meter cells. That means that would be 100 cells by 100 cells to complete that space. We have a minimum value for the porosity we're working with is 4%, and we have a maximum value of 16%. The color map we're going to work with is one of the built-in color maps available with matplotlib pyplot, which is our PLT. The CM are the color maps, and plasma is a good map to work with because of the fact that the intensity varies with the magnitude along with the color, and so folks who have color blindness issues and so forth are often able to work with this color map. We're going to use the pixel plot program, which was one of the functions we declared above. It is one of the geostats pi functions, which re-implement commands directly from geoslib. Now, in this case, we're re-implementing just by using matplotlib in order to do that, and the inputs are very similar to the types of inputs that you would have on the pixel plot program. We can go ahead and run that program, and if we do that, we now see, in fact, what the porosity truth map looks like. That map that we just loaded in. It's 100 by 100 values, porosity between 4% and 16%, plasma color bar, pretty stunning. You can see how that color map or color bar is pretty convenient and should be pretty good for somebody who had challenges with seeing between different colors, tones, and so forth, that the intensities are varying with the colors, and so that would work well with people with a variety of type of sight issues. So now let's go ahead and do a couple more things with our ND arrays. I think we've covered the topics of loading and writing and visualization. So one thing is you might want to just look at your array. You can do that. You could just type the name of the array, you can type the print command in and just type the name of the array. And if you do that, you can see a truncated representation of the two-dimensional array. You'll see that this is a single row right here, individual columns, and they're all surrounded. Each one of the rows is encased in the square brackets. The overall thing is encased in square brackets. So that's pretty useful. You can also access a single slice within the array. And so if you want to see a slice along a specific Y value, so get a single row, you can go ahead and do it like this. And so if you were to count these up, you would find that there's 100 values that you're in fact seeing the very first row. And so you'd see these values match up. And the last value is this value down here. And so you're seeing all 100 values from the first row. That's what happens if you put one index in. Now, if you put in two indices, now what's happening is you're going to see a single value, the first row, the first column, the first row, the last column. And so if you do that, look at that. Okay, so this value here was the very first row value right here, the first value in the first row. This value right here is the last value in the first row. And so we can get in and surgically start to find specific values in our two-dimensional map, and we can access them like this. Now, you might find that that notation is sloppy, that there's so many brackets, it drives you nuts. So you can do it like this. Just use a comma instead. It's a bit more truncated, or it's a little bit more concise as far as describing or addressing those values. Now you can also do all kinds of slicing. For the first row, you could get the first 10 values from the first 10 columns. Now remember, the convention will be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and not the 10th value. And so you'll get 10 values like that, the first 10 values. And if you run that, there they are. You can go back up here and you can confirm that they in fact are the first 10 values from that set. So we can do all kinds of slicing by using the colon again, just like we did before. Now, as I mentioned before, you might want to look at the entire array. Maybe you're feeling brave. Maybe your array is small enough that you think it's fine to go ahead and just visualize it. Within NumPy, you can set the print options, set the threshold to not a number, and when you do that, it will print the entire array. And so if we do that, when we run that block, you'll get back this. And so here it is. 10,000 values, row by row, each row with 100 values, 100 rows of that. And so it's all there. Okay? So if you were interested in looking at all the data values all at once, you could force it to do so like that. Now previously we had loaded up the stats functions from SciPy. And so these provide some really powerful methodologies to get at summary statistics from our information. And so we can go ahead and use the stats function describe in order to do what we did with the data frames where we were getting summary statistics, but we'll do it on an ND array. Now the ND array will flatten it. We don't want to get stats by each of the individual rows. We want to get it over the entire model all at once. So if we run it, this is what we get. We get the number of observations, the min and the max in a tuple, the mean, the variance, the skewness, the kurtosis, and so forth. So this is pretty useful to get all these summary statistics just with one command. Now you might want to do your own thing. You're kind of independent. You want to build your own summary statistics outputs. And so you'll find out that there's a whole bunch of different functions for ND arrays which will go ahead and calculate the summary statistics over all of the entries in an ND array. We got the mean, the sample standard deviation, the min, the max, and so we can go ahead and run those functions, and we can look at them right there, and we can compare them to what we got before, and we can see in fact that these are the values that we get. That's pretty useful. So you might decide that you'd rather work with the NumPy functions that specifically calculate these statistics, and so there's another variant here. Rather than going to the ND array functions, we just go to the general NumPy function. So NP, mean, put the ND array in, NP, standard deviation, sample standard deviation, min, max, and check this out, percentile. Now the cool thing with a lot of things you do in Python, you'll find that you can sometimes substitute a tuple for a parameter. And so this is porosity map, give us a specific percentile, and we put a tuple in, and now what it'll do, it'll create two outputs all at once. We'll get the P10 and the P90 each at the same time, and we can go ahead and look at those. So voila, we have the whole thing super easy, and we can get our summary statistics like that. Let's just have a little bit of discussion around checking and manipulating our data. And so the first thing that's useful is we want to be able to read, and we've shown this before, but we'll get into this a little bit more detail, read and write individual values within our array. Now, our array has indices going from first IY, 0 through NY minus 1, and then the other one's IX, 0 through NX minus 1. So IY, IX. And so we can say, give us the first value, so from the first row and the first column, and then let's report that. Then go ahead, set that to 10% and report that by writing out the value at that location, not the value constant that we set it, but tell us what the value is, just confirm that it's been set. And so if we run that command right there, the value in the first row, the first column of our two-dimensional ND array was 9.47% porosity. But now, after we've set it like this, it's now 10%, and we're actually reporting the value at that location, converted to a string, appended into our string within our print command, but that's what we've done. Now, just like with data frames, we can use the NumPy nan object, which is not a number, for missing values. And let's go ahead and set the very first value, the first row, the first column, to not a number. And if we check what happens, this is what happens. The location 00, the ND array, is now nan, and it's reporting that right now. So we can go ahead and do that. Now, you might be interested to check if you have any nans within your array. This would be a good thing to do within data checking and cleaning. So we're going to add a couple more nans, not a numbers, into our missing data, into our two-dimensional ND array. We do that with these commands right here. Super easy. We're just within the first row and within the second column, set it as nan. Within the third row and the second column, remember everything goes from 0, 1, 2, 3, and so forth. So second column, set it to nan. And then what we'll do is we'll do a little check. And we'll say, well, use NumPy's isNan function on this and just report to us if there's any. Do we have any of these nans? And so when we do the check, it says, yep, you've got nan values in your array. And then we could say, well, I want to get a list of where these nan values are. I want to find out the indices of where these nan values are. So NumPy has a command that we can use where it'll find out where something occurs. And once again, we use that same command and say, well, where are there nans? Are there any nans within this? And this will say, well, give us the indices for where that happens, and then we'll print out those indices. So when we run that, look at that. Cool, eh? 0, 0, so the first row, the first column, the first row, the second column, and the third row, and the second column all have nans, and that's exactly where we put them. It's almost like a magic trick, a magic show, right? I'm kidding, but it is super easy to do, super cool to find them, right? And so we can go ahead and take that those nan lists, and we can map it onto a tuple, turn it into a list. So now it's a proper tuple list. It's going to be a list of coordinates that we can use. And so when we do that, this nan list, we can now use that with its indices 0, 1, 2, 0, 1, 2, and we can apply that directly to porosity map and get the values, access the values, change the values. Well, first let's access the values. This is super cool. So this is just reformatting, taking this nan list, mapping it to tuple, and creating it into a list, and this is what we get. This is our list of tuples, and if we print the values for the list of tuples for the very first tuple, 0, which will be 0, 0, we get 0, 0, and the value there is going to be nan. The next one will be 0, 1, 0, 1, and it's nan. So this works. We've now converted our list of indices to something we can use to actually directly go to our porosity ND array and grab values. Now, can we write values too at that location? You bet we can. So now this is a very simple way to replace the null values with a default very small porosity value. Let's go ahead and just make them 0.1% porosity. And so we go ahead and we use the nan list, a list of tuples, and we can go ahead and say 0, 1, 2. Well, we could use a loop, but we won't do that right now. And you can confirm that if we do this, we can reset those values to in fact be the value at the first nan indice after setting it to 0.01 is that value. And look at how we did it. We said the matrix, the two-dimensional ND array, the nan list tuple index 0, so the very first value. And we can see that in fact it has been reset from its original value of nan to now a value of 0.001. So we now were able to find not numbers or missing values, get their indices, reformat the indices as a list of tuples that we can then go and use to grab the values like here, or rewrite the values like we did here. Okay, how do we make arrays? Well, if you look up ND array Python, this is what you'll find. You'll find that the simplest way to make an array is just use the command numpy or np.array and just specify it like that. Now, what kind of array is this? It's going to be a a 3x3 two-dimensional array. And so let's go ahead and check it. If we go ahead and run this line, we got a 3x3 array. What do you think that array looks like if we tried to take a look at it? Well, its name was my array, and we could go ahead and now you'll notice we'll only write out when we do Python the very last thing. This, we don't see the shape anymore, but of course if you wanted to, this is just a little bit of an aside, you put a print in to force it to also show that, and now we'll see both things at the same time, and you can see the array. It's a 3x3 array. So this simplest way to make an array. Now, there's other ways to make arrays too. One way is you have a set of different numpy commands that will build arrays. For instance, the random.rand, and you can put in n, x, and y, will create a two-dimensional array with random values. And that's pretty useful right there. We'll check to see what the shape is. We'll look at the summary statistics of it, and we'll do a plot of it all at once. The numpy np.zeros command will create an array too. And notice that here we have to specify the dimensions, the 100 by 100 array, two-dimensional array, as a tuple. So we put it in brackets. If we don't do that, we'll get an error. And we can check the shape, we can check the statistics, and we can create. So if we run that, let that run, we get the summary statistics. For the first case, we got the array of random values. We got the mean, we got the variance, skewness, the min, the max value, and so forth. The random values here are clearly going between 0 and 1 with an average of 0.5. And for the zeros, we get something that's completely uninteresting, just zeros at every single location. Okay, let's look at some operations that we can use on arrays. So we got our two-dimensional array, our porosity, underscore map, our 2D array. And what we want to do is we want to find all of the values, the nodes, that are greater than 15%. This command creates a list of all of the porosity values that are greater than 15%. The way it does it, this part right here, porosity greater than 15, creates a Boolean array of the same dimensions of the original porosity map. If we apply that Boolean array back to porosity map, it's going to extract only the values that are true. And the result is we get greater than, which is going to be only those values within this porosity map, that within the original porosity map, that are greater than 15%. Therefore, if we calculate the size of that array, a one-dimensional array, list of values in 1D, we'll find out that that's the number of cases greater than 15% of the total original values, which is to just be porosity map flattened. Its size will be the original 10,000 values. Let's go ahead and run that and see what happened. Here's a list of all the values with porosity greater than 15%. There are 25 values in the porosity map that are greater than 10,000. Now we can also plot the Boolean array to get a map of the nodes that meet this criteria. And so, as I mentioned before, this type of inequality here results in a brand new two-dimensional array with the same dimension of this one, with a true every place where this is true and false otherwise. And we can go and plot that to get a sense of what that looks like and to understand it. And so let's go ahead and just give that a quick plot. And if we do, all of the locations where we have a true are reported as 1. All the other locations are reported as 0, as blue. And you'll notice that there's a little bit of orange, kind of reddish colors here. That's simply interpolation going on with the plotting methodology. And so this is pretty fascinating. We're able to actually see that we can create a new Boolean array just by using a command like this. Now we have a numpy command non-zero that will take that Boolean array and will actually give us all of the indices at which we have true values. And this is extremely powerful because this becomes a list of all of the locations for which we have high porosity. So we create our Boolean array for all porosities greater than 15%. We use the numpy non-zero command, and the result will be a list of the locations. And so then we could access that list of locations by just simply saying, okay, location 1, Ix is going to be equal to the locations of high porosity, this array right here. Location 1, the first column is going to be 0 for the x for the y values, 1 for the ix values, and this will be indexed 0 through number of locations that we find. And so we go ahead and run that command. We'll find that the first location with a porosity greater than 15% is Ix equal to 82, Iy equal to 34. Second location, and so forth. And so using this method, we can get at all the locations that meet a specific criteria. We could replace those values. We could summarize them with statistics. There's so many different things we could do with them. You might be curious about what exactly this thing looks like, location high porosity. If you run that, you can see immediately that it's simply going to be two sets of arrays, one-dimensional arrays. These are all of the first is going to be all of the y values. So in other words, the rows, these are the columns, and so 34, 82 is the first case, 37th and 88 is the second case, and so forth. You can read across like that. So you might find yourself wanting to do something more creative. There might not be a built-in function with NumPy to be able to do exactly what you want to do to your array. You can loop over the array, performing mathematical operators on each one of the individual elements within the array. Now, I should warn you, that's slower. The NumPy built-in functions for working with arrays, such as calculating the summary statistics and so forth, are optimized to be fast. These types of methods will slow your code down a bit. So, If the array is small enough, you may be able to still do it. This is brute force. So let's give ourselves an array. It's going to be an array of zeros. And we're going to say, let that array be equal to the original porosity values from the porosity underscore map plus a random value. And so that random value was declared within a previous random array that we constructed before, but it had a mean of 0.5. Well, that would create a bias, so we'll subtract that out. And we don't think that there's enough magnitude to that random value, so we'll multiply it by 5. And so what are we doing here? We're taking our original porosity data and we're adding noise to it. Now, of course, we could have actually done this, and I'll show below in a more efficient manner, but I just wanted to demonstrate the idea of brute force. And so let's go ahead and do that, calculate the summary statistics, and create a plot. Now, I have to update this really quick because this was something that changed recently, but I can go ahead and run it now. And there we go. And so if you look carefully, what you're going to see is that there's random at every location, random noise, but there's still that background of features from the original porosity map image. And so this worked well. In addition, you can go ahead and look at the mean value. It hasn't changed. We added a residual with a 0 mean, so we have not changed the global mean. We will have changed the variance. I think the original variance was around 4 or so. We could go back and take a look. It has been increased. Okay, so now how else could we have done this? Well, what did we do? We took the porosity map, we added the random values, subtracted the 0.5, multiplied by 5. Without looping, we can use, if we use ND arrays, we can do our math just like this. Array 1 plus array 2 subtracted from a constant, multiplied by a constant. That's easy to do, and this will be optimized. This will work very fast. And then we can do the summary statistics on the result. And okay, so we run that and look at what we get. If you look at the summary statistics and you look at the maps, they're indistinguishable from each other. Now let's just finish up with writing our result. Maybe we like our new map with noise added, and we're going to save it to a GSLib file. So that would be a two-dimensional array saved as in a GeoEAS format. And so this was the name of our 2D ND array from NumPy. This is the name of the file, and this is the name of the property that we're going to save. And we can go ahead and run that line of code. If we do that, we've just created this property. And if we wanted to, just for completeness, we could load that property up in TextPad. And this is what we just made. This is the standard GeoEAS format, which is used by GSLib. The name of the file, the number of columns, the name of the property, and then the values, all sorting, first of all over columns, then over rows, going from bottom to top. Okay, so that completes this demonstration of ND arrays. I think this is enough that people should be able to get started with working with gridded data within a variety of different operations and methods, to feed them in as inputs for other numerical methods, and to be able to, in Python, build workflows for subsurface modeling. All right, I hope that this was helpful. I'm Michael Perch. I'm a professor at the University of Texas at Austin. I'm the Geostats guy on Twitter. Also on GitHub, I have a variety of files and resources available, and I hope this was helpful. All right, take care.